G'day viewers. In this segment I'm going to talk about firewalls. So firewalls are very useful network devices that protect a local network from all of those hosts out there, other hosts out there on the internet. They're also very interesting to us from a security point of view because they protect the local host by really restricting IP connectivity rather than using cryptographic measures as we've looked at before. Okay, so let me start with a little bit of motivation. Say here the best part of IP connectivity is that you can send packets to any other host on the internet. That's really been a key to the success of the internet, so it's wonderful. Well, the worst part of IP connectivity, guess what it is? Any other host on the internet can send packets to you. Even hosts which are nasty, which you don't like, and there's certainly a lot of nasty hosts and strange traffic out there, which you wouldn't necessarily want on your own network. So let's move to a goal and threat model here to understand what we're trying to accomplish. Well, with a firewall, our goal is to implement some kind of network boundary at the entrance to your network, your home network or a corporate network, that restricts IP connectivity so that you can talk to a host on the public internet just as you want it, but Trudy is kept out. Trudy is unable to talk to hosts on your local network. So ideally, we would like to obtain a picture like this. Ideally, we want to partition the internet in such a way that Trudy is kept over here on one side. There's Trudy with all of her bad packets, and you were able to use the internet and talk to the host you actually want to talk to just fine. That's what we would like to happen. Of course, it's going to prove to be a little difficult to get just this to happen. So let's see how we might go about doing that. Well, a firewall is actually a kind of middle box. So I want to just show you this slide again and have you remember how middle boxes work, because that will tell us most of what a firewall is going to do. So a middle box, and this device here is a middle box, is a device which sits logically inside the network, so it's occupying a position almost as if it were a router. Yet, unlike a real router, it's performing more than processing at higher than the IP layer. It shouldn't be. That's this strange bit here. It shouldn't be because it has no clean way, according to our layering model, to operate beyond the IP layer. But it just does because it's a convenient way to add new functionality that couldn't easily be added otherwise. In the case of a firewall, this device will be looking beyond the IP layer to filter packets and decide which packets are allowed into the local network and which ones aren't. And we've already seen a nice example of a middle box, and that is a NAT box. Firewalls or intrusion detection systems are often other examples of middle boxes. So let's go a little further and just look at our protocol layering diagram to help us understand what's going on, to see how a firewall fits in as a middle box. Okay, so here we have an organization. If you like, this is a local network. This is like your network, the network you want to protect. So you have hosts on the inside here, and we have one here, and they have a regular protocol stack, and they're just talking to hosts on the rest of the internet, just as usual. But of course, there are two kinds of hosts out there. There are hosts that you want to talk to. Great, you should talk to them with all the normal protocols. And then there are hosts that you don't want to talk to. That's Trudy. So the job of a firewall here is to act as a kind of router. So this is the usual router functionality. But in addition, look inside packets at the transport and higher layers, possibly all the way up to the application, to filter packets so that we let through packets from the good hosts, packets that have been sent from us to and from the good hosts, whereas we get rid of packets that have been sent to and from the bad hosts. This will make it look like the bad hosts can't even be reached as though they're not on the internet. This is what we would like a firewall to do. And if we accomplish this, then they won't be able to send us nasty packets, with all sorts of viruses and nasty content. So zooming in on the operation of a firewall a little more, here's the firewall device here. And you can see that it has two sides. The internal side, that's the organization, and the external side, that's the public internet. The job of a firewall is to relay packets, as a router would, between these two sides, but for each packet, since a firewall must operate at the packet layer to forward packets, for every packet that tries to cross from one side to the other, actually in both directions, I've drawn the incoming direction here because this is the one that people would intuitively most care about. They would care about how packets from the public internet can enter their network. You might also care about restricting connectivity in the other direction to make sure your hosts don't contact strange computers. But let's just look at the incoming direction. For every packet that comes in, the job of the firewall is to make a decision. And the decision is whether to accept the packet. And to do that, you'll simply pass it unaltered, and the packets and the hosts that are communicating won't even know the firewall is there. Or you could decide to deny that packet, in which case you'll simply discard it silently without sending error messages anywhere. And to the two hosts that are involved, it will look like the network is broken, there's no connection. You can see this is why middle boxes have some strange effects, because we now have a bit of a strange model where connectivity might work sometimes and suddenly vanish. It's okay if it vanishes for the hosts which we didn't want to talk to, but if it ever vanishes where you wanted to talk to a host for some reason because the firewall's not properly configured, it can be a pretty strange sort of error to find. So the key task for us is really to make this accept-deny decision. What packets should we accept or deny? Well, this is actually a local policy. Oh, where's my pen gone? This is actually a local policy. It should be set up according to how you want to run your site. And really that you could think of the firewall here as centralizing the IT job so that people who are administering the network would have a nice central point of control to inspect and get rid of unwanted packets as they enter or leave the network. So the key design decision in firewalls is to decide whether to accept or deny packets as they transit the firewall. And there's a key tension there. The key tension is that we need to be able to translate from policies that people would like to implement to decision rules that we can implement on every individual packet. The tension is that policies are really relatively high-level statements for what we would like to happen. Usually they'll relate to the kinds of apps you can use and the kinds of content that could go through the firewall. On the other hand, packet filtering is inherently a low-level operation. It occurs for individual packets, so we're operating at the network layer. This means that we have a limited viewpoint into the network. You don't directly get to see the application messages, for instance, because they may be spread across many packets. And in fact, if high-level encryption is being used, then you won't even be able to peek inside the messages at all. Well, so there are several different kinds of firewalls that implement decisions in slightly different ways. And I'm going to tell you briefly about each of them, starting from the simplest and working up. The simplest kind of firewall is a stateless firewall. It really has very simple static rules, which are packet filtering rules. Now, you can only filter on the attributes of packets, so typically these rules will use things like TCP, and UDP ports as you peek inside the packets as they go through the firewall. This will allow you to do things like, you'll be able to allow or disallow different kinds of services or destinations across the network and so forth. An example rule is shown here, deny TCP port 22. I happen to know port 22 is the port that's used for telnet. So with this rule, you would disallow telnet connections from outside the internet or between the public internet and the hosts on your private network. That might be a policy you would want to implement for security reasons, so no one could remotely access command lines on your different hosts. But this is all fairly, it's a static rule set, so it's only good for implementing a few kinds of decisions which can be expressed statically for every packet. Let's take a step up, and you have what's called a stateful firewall. A stateful firewall implements the same kind of packet filtering rules. We're going to look at the attributes that are on the packets, but we will allow some kind of state to track the exchange of packets and model what's going on and make decisions according to that. That allows you to make various kinds of if-then rules. In fact, we've already seen a good example of this, a NAT device. A NAT device is a device which, as well as doing the address translation, allows connections to be made from an internal to an external host, and if that has happened, then it allows the following packets from external hosts on the public internet that correspond to the connection back into the private network or the local network. So you can see that a NAT box is implementing this kind of if-then rule. If a connection's been established from the inside, then allow packets in from the outside. That's the kind of thing you could do with a stateful firewall, whether you did address translation or not. And another step up to the top level here is an application layer firewall. Really, an application layer firewall here tries to implement rules that are directly based on application usage and content. The kinds of things, the high-level statements we wanted to make for policies. For instance, you might try and inspect the contents that's coming into your network to look for well-known viruses and chuck any packets that contain viruses. Well, to do this, we have a bit of a problem because firewalls operate at the packet level and application messages which carry content may be split across many packets. So an application level firewall, because it tries to look beyond packets, it's going to have to emulate things that hosts would do, for example by reassembling many IP packets and looking at the application messages that are carried in those packets. Because it's only by looking at those application messages that it will be able to decide whether there are viruses and so forth in it. So an application level firewall is trying to operate at this high level. As you might imagine, that's somewhat of a difficult task and it can only be done imperfectly and with a fair bit of work. But where you can do it, you maybe find a way of shielding your organization from viruses and other undesirable high-level actions that couldn't otherwise be expressed in terms of individual packet characteristics like TCP and UDP port numbers. And finally, to finish with firewalls, I'd like to talk briefly about deployment. Here is a classic deployment scenario. Actually, in all of the cases, what you're going to want to do is place a firewall around the internal-external boundary. So where your organization meets the public internet, at all of those places, you would want to place a firewall to control the traffic that's going across that boundary. Now, so we have here in this classic picture, we have an internal network and an external network, which is the internet. Here's the boundary between internal and external. In a classic setup, you'll, in addition, also often have what's called a demilitarized zone, or a DMZ. Here's the DMZ between the firewall device, which is here, and the external internet. So the DMZ is like the last bit. It's outside the internal network, but it's within your organization, not the external internet. The reason you might do this is you could put hosts inside the DMZ, such as your web server or email server, chatty hosts that talk a lot to other hosts on the internet. This way, you could, if these hosts were ever compromised from the connections they had to make, then you could prevent connections between these hosts and other hosts on your network here, because you could chop this off with your firewall. So if in the worst case that your web server did get infected, you could prevent an infection from spreading from there to your other hosts on your network, maybe your more sensitive hosts, because those other hosts were behind a different firewall, even though both the web server and the other hosts were both in your local network in some sense. So that's how our DMZ can help provide better separation between the external internet and your precious internal hosts. And as a final note on deployment, I would say that firewalling technology is now being built into many different devices. So we have various options in how we would deploy it. It always fits this picture I've talked about in terms of protocol layering, of operating logically at the IP layer, even though it peeks at other things. So it sits like a router. It could either be deployed as a specialized network device like a router. That's what we saw in the previous picture with a classic firewall and a DMZ just beyond it in the internal internet. Firewalling technology can also be built into other devices which sit at the boundary. A good example here is your AP, your wireless access point. That usually sits between your home network and some kind of wide access like cable or DSL to the rest of the internet. So it's a good place to implement a firewall. And so a firewall is often built into your AP these days. And in addition, you could, or instead, you can actually do them both. You can also imagine that firewalling technology can be built into the network layer of individual hosts. This is as part of the OS. So many OSs today will have firewalling technology built into them. It's doing the same thing we've talked about, it's just it's moving it down to the host level to provide more protection. In fact, there's a little bit of a trade-off here. As you might imagine, that putting a firewall in the one spot, like in your AP, where you go into your local network or leave it, it can centralize things and it can simplify your job of your IT job, because it's centralizing the policies which you use to accept or discard packets. On the other hand, distributing the implementation of the firewalls to all hosts has other advantages. It actually tends to improve the protection. That's because if one host on your network is compromised, you still have the firewall between it and another host on your network. Whereas if you just have it at the boundary, once you get past that firewall, you can roam freely amongst all of the hosts in your network. So distributing the implementation of a firewall actually provides better protection. It can provide better visibility into apps, because a firewall on your local host can know what applications are actually running and sending the traffic. It doesn't have to guess from the TCP and UDP port numbers. Applications like Skype, for instance, don't use a well-defined set of port numbers, so it can be difficult to know if packets actually come from a Skype application or not. If you're running on the local host, presumably your operating system has a very good idea what process generated the packets, so it can know if that's the Skype implementation. And even in terms of performance, a firewall running at every host is gaining the performance advantage of having many hosts implemented in parallel, rather than one firewall which has to be a very high performance host. So you can see this as an interesting trade-off, and I would expect that we'll see a greater use of distributed firewalling technology over time, with the application of centralized policies to make it more manageable. Okay, so there you go. Now you know about firewalls, what they try to achieve, and how they operate.